Today we have Monica Russell here presenting her presentation on evaluating hypoxia, the accuracy of peripheral oxygen saturation measurements with Polar Elixir, and the variability in individual responses. I am really nostalgic as I introduce Monica today because not a lot of years ago, we were both sitting in this room attending the seminar class, which a lot of the undergrads today here are, and now she's presenting and I'm introducing her. So Monica is an applied research technician at sport product testing at the Canadian Sport Institute here in Calgary, Alberta. She did her Bachelor of Science with a specialization in biomechanics at the University of Calgary, after which she went on to pursue a Master's of Science degree in biomedical engineering under the co-supervision of doctors Brent Edwards and Carolyn Emery. When Monica is not busy doing data collection and analyzing data, she spends her summers hiking and getting ice cream at Made by Marcus, and her winters snowshoeing and also getting ice cream at Made by Marcus. So if you ever need to find Monica, you know where to go. And now I will hand it over to her for her presentation.
Thanks so much, Ashna. Yeah, this is pretty nostalgic, isn't it? I'm crazy. So I know quite a few people in this room, and I don't know quite a few people in this room, but the people that I do know are probably a little bit surprised to see me up here presenting on hypoxia and not biomechanics. I'm also surprised that I'm up here doing that. But that's the beauty of working with sport product testing over at CSI. You kind of get to dip your feet into a lot of different things. So I'm gonna present on this project that I was able, given charge with, and I'll show you guys what I learned and hope you learn something as well. So if you aren't familiar with sport product testing, we are a independent unit within the Canadian Sport Institute of Alberta. And we objectively extract meaningful and relevant insights so that more accurate and usable products can be available to consumers. And we carry out product testing, validation studies, usability testing, and just kind of general research across sports, fitness, health, and technology markets. Our clients include global brands like Polar Elixir, with whom SPT has conducted validation and usability studies since 2015, so almost 10 years now. We've done 2 optical heart rate validation studies for Polar, one on the A360 fitness tracker, and then one on the M600 smartwatch, which John, in the audience here today, published a paper in MSSE in 2017 on that M600 device. But more recently, we did the SPO2 sensor validation study for Polar. We aided in the development of their algorithm prior to the launch of the Polar Vantage V3 about a year ago now. And we also published a paper in MSSE this month, actually, it just came out, very exciting. So that's what my talk will be focused on. So that being said, this project was funded by Polar, and our the ethics in the study was approved by the UFC and Mount Royal Ethics Boards. So a little outline of my talk today. We'll go through some background and objectives of this, of the paper that was published, as well as a side project that we did off of that. We'll go through the methods, and then project 1 is that paper that just got published, so we'll go through the methods and results of that, and then this little side project that we tacked on, I'll go through briefly at the end as well. So to start, what is hypoxia? If anybody was at Trevor's talk last week, he did a great talk on this, but if you weren't there or if you forgot it already, I'll give you a little bit of a recap. Hypoxia is defined as a deficiency in the amount of oxygen reaching the tissues. So this occurs in one of 2 ways. The first being reducing the fraction of inspired oxygen, which is called normobaric hypoxia. So the pressure of the air that you're breathing stays the same, but the amount of oxygen in that air is less. And then the other way to do this is reduced atmospheric pressure. So that's called hypobaric hypoxia. So the pressure of the air around you is less, so therefore the pressure of the oxygen that's in that air is also less. And so both of these eventually reduce the oxygenated hemoglobin in your blood or your SaO2. So what is SaO2 to start? The A stands for arterial, so it's the saturation of the blood in your arteries with oxygen. This is the gold standard measurement of blood oxygenation. It's comes right from the source, you can't get any more exact. That being said, because it comes right from the source, it's quite invasive to get. you need an arterial catheter, pulling blood right out of your arteries. So I'm sure we've all had a venous catheter where you get blood taken out of your vein. The arterial catheter is much different. And that being said, this can only be performed by certified personnel like anesthesiologists, respiratory therapists, and other physicians. So that brings us to SpO2. The P stands for peripheral. So this is a peripheral measurement of SaO2, basically. So although this isn't the gold standard, there are many medically approved SpO2 devices, such as the fingertip pulse oximeter that I'm sure you guys have seen in hospitals or clinical settings. And so these SpO2 sensors are wearable, portable, more affordable, non-invasive, and therefore they can be kind of used by anyone rather than very specific people. With that being said, why would you even want to know your SpO2? Why would we buy an SpO2 sensor to use ourselves? And there's multiple reasons why, but I'll go through a couple here. One of which is for diagnosing and monitoring sleep apnea. So you can wear an SpO2 monitor when you go to sleep. And if you have sleep apnea, you would get different values recorded there, and then physicians can diagnose and monitor that condition. Similarly, respiratory diseases, just coming out of COVID, if you have a respiratory disease that kind of impedes your ability to breathe, your SpO2 saturation might also be affected. And then the final one would be altitude training, or just or staying at altitude. You want to see what that hypoxic environment might do to your body. So that brings us back to Polar. The SpO2 algorithm sensor validation study was brought to us by Polar because if you haven't heard of Polar, they're a very established company in the heart rate monitoring space. So a lot of exercise physiology labs use Polar heart rate straps in their labs. But up until a year ago, they didn't have any blood hemoglobin oxygen saturation sensors on the market. So they came to us and they wanted to do a validation study specifically following the International Organization for Standardization protocol, which calls for a controlled desaturation validation study. So here's the paper. And the two objectives of this paper, of this project, were one, to evaluate the accuracy of those SpO2 measurements from the Polar Elixir pulse oximetry technology on the wrist, compared to the SaO2 values from the blood draws during acute, stepwise, steady state inspired hypoxia at rest. And then a post hoc objective was to determine if we could improve those SpO2 measurements by recalibrating the algorithm using some of those SaO2 values from a random subset of participants. So here's getting into our subject demographics. We had 28 people graciously volunteered to be part of the study, average age of 28 years old. And then this histogram here on the right side shows the distribution of skin tones that we had in this study. They were all self-reported. So we got all of our participants to identify themselves on this Fitzpatrick scale, with 1 being super, super pale, 6 being quite dark. And this is because literature has shown that the shade of your skin actually impacts how optical heart rate monitors work. So the amount of light that goes into and gets absorbed by your skin is impacted by the color of your skin. So we wanted to try and recruit across a range of those skin tones. And so looking at our distribution, we kind of think that this is the right around the accurate distribution of the population of Calgary, which is good. Okay, so getting into this controlled desaturation validation study protocol. The ISO protocol requires 3 main criteria. The first one being there's paired observations of SpO2 and SaO2 values over the specified SpO2 accuracy range. So for us, that was 70 to 100% SaO2. And then the second is the fraction of inspired hypoxia, or FiO2, delivered to test subject is varied. So that's how we achieve those lower SaO2 values. If you guys remember from the beginning, that's normal baric hypoxia. We're keeping the pressure the same, but we're reducing that oxygen content. And then the third one is arterial blood samples are periodically taken from an indwelling arterial catheter. So here's a little schematic of our protocol here. We've got time on the x-axis and we've got FiO2 on the y-axis. So you can see we start at the beginning there at 0.21 FiO2, which is the same as 21% oxygen, which is what all of us are breathing right now. And we take 5 blood draws, and the SaO2 of the participants is around 97 to 100%. And then we change the FiO2 and bring it down to 0.18 or 18%. And then we wait 4 minutes for the participant to come to steady state. We take 5 more blood draws. SaO2 is around 90%-ish right now, depending on the person. And then we change the FiO2 again, 16%, same thing, and then 14%, and then 12%. And 12% is approximately Everest base count for reference, so that's kind of fun. And then once we take those 5 blood draws, we bring them back up to ambient air, back to 21%, just monitor their vitals and make sure they're coming back to normal. Here's some photos of our setup. So all of our testing took place in the exercise physiology lab over at CSI Alberta. So this is one of our participants lying on the bed with our anesthesiologist on the right there, monitoring their vitals. And then they have an anti-static blanket on for warmth. On the one hand, we've got an arterial line in the wrist for blood draws. The side was determined by the physician. And then behind the participant there, we've got the mouthpiece in the participant's mouth connected to Douglas bags, and they're all filled with pre-ordered mixed gases, nitrogen and oxygen. We have 18% oxygen, 16, 14, and 12, like I showed you in that schematic. And then on the other wrist, we had the Polar Elixir device, which was set up by our researchers on the wrist without the arterial line. And then behind the participant, we had a lab chart open, which was an application we used for monitoring vitals like heart rate and SpO2. And we used it to insert event markers when the blood draws occurred as well. And then finally, in the very back of the room, we had our little blood station. So immediately after a blood sample was taken, it was labeled and analyzed using an IStat machine. Okay, so getting into the analysis, we have 2 parts that correlate with our 2 objectives. So the first one being the validation part. We want to validate the algorithm that they gave us. And then the second part, part B, we want to see if we can improve the algorithm with that SaO2 data that we got. So part A, we compared those SpO2 values from the Polar Elixir to the SaO2 values from the blood. So this figure shows a sample participant data. This is a SpO2 data from the Polar Elixir. So you can see it kind of starts around 95% and dips down to around 78%. But this is basically just to show you, we have black vertical lines for the where the blood draws occurred. And we took a 7-second average of the SpO2 data from the Polar Elixir around each blood draw. And that was mostly to account for differences in timing and syncing of the signals. And then we assessed the accuracy of the SpO2 data compared to the SaO2 data using 4 different stats methods, one being root mean squared error, another being interclass correlation coefficients, and then we use Bland-Altman plots and correlation plots. And then moving on to part B, like I mentioned, we want to try to use the SaO2 values to recalibrate the SpO2 algorithm to make SpO2 calculations more accurate. So to do this, we took the original data. You may notice that it's an N of 25 rather than N of 28. We had 3 people whose watch data kind of malfunctioned, so we excluded 3 participants. And we split the final 25 included in the analysis into 2 groups randomly. We sent half of the data to Polar as the calibration set, and they recalibrated their SpO2 algorithm using SaO2 data from those 13 participants. And then after that, we had our test set of participants who we didn't send the SaO2 data to Polar for, and we reran the SpO2 algorithm on those participants to reassess the new accuracy. And then again, we ran root mean squared error, interclass correlation coefficients, Bland-Altman, and correlation plots. So just so that we're all on the same page, don't know what everybody's stats knowledge is, so I'm going to run through briefly what all of these are. So RMSE is a measure of the absolute difference between predicted and actual values, or the standard deviation of the residuals. The residuals are those little red vertical lines between the data points and the line of best fit there. Interclass correlation coefficients are a measure of how similar values in 2 clusters are. So in our case, SpO2 and SaO2 data, and it'll give you a value between 0 and 1, with a value less than 0.4 being poor agreement, a value between 0.4 and 0.75 as moderate, and then a value greater than 0.75 as excellent. So Bland-Altman gives you a plot as well as an analysis. So the plot is a visual representation of the agreement between 2 measures of the same metric. So for us, we have the mean of 2 measures. So we have the mean of the SaO2 and SpO2 on the bottom, the difference between the 2 measures on the y-axis, and then we get a mean difference or bias in the blue line here, and then we get limits of agreement denoted by the red lines. And those limits of agreement contain 95% of the differences, between the two measures. And then finally, I think we're all pretty familiar with correlation, but it's a visual representation of the relationship between the two variables. And then you can quantify that linear correlation using the Pearson correlation coefficient. And you may ask why we did so many stats. They're kind of all pieces to the puzzle. And if we had used any single measure on its own, it wouldn't have given us a full story. So if we had used just correlation, we can have a really strong correlation, but that doesn't mean that it's a very accurate device. So we wanted to try and cover all our bases and have a really comprehensive story. So looping it back to the ISO protocol itself actually has guidelines for how accurate a pulse oximeter, how you can deem a pulse oximeter to be accurate, I guess, sorry. So their threshold is a root mean squared error of less than or equal to 4%. And then they also want you to provide root mean squared error values for smaller ranges, so not just 70 to 100%, but also 70 to 80, 80 to 90, and 90 to 100% SaO2. Okay, so getting into the results now, this figure is the first figure in our paper. There's a lot going on, so I'll walk you through it here. In panel A, we've got blood draw number on the x-axis. We've got FiO2 on the y-axis. So we're basically trying to confirm our hypoxic stimulus. So we're just making sure that across all participants, because that's a mean of all the participants, that we gave them 21% oxygen first, 18% oxygen second, 16, 14, and then 12. So you can see the standard deviation bars are very, very small, which is good. This panel B here shows SaO2 on the y-axis in percent. And so you can see we start, this is the mean across all participants again. We start around 97%, and then we slowly drop down to on average around 75% at that 12% oxygen step. And then finally, this last panel, panel C, is actually just a sample participant, but this is comparing measures. So we've got our blood draws as the red asterisks there, connected by a line. And then we actually had one of those fingertip pulse oximeters on participants so that our anesthesiologist could monitor SpO2 in real time during the data collection. And so we thought it'd be interesting to plot that on here as well. So we have the fingertip pulse oximeter in green, and then we have the Polar Elixir SpO2 data in blue. So we can see that the more hypoxic we get, the more the Polar Elixir tends to overestimate a little bit. And this trend, even though this is only a sample participant, this trend was observed across all participants. This is just for visualization purposes. Okay, so getting into all our stats. So root mean squared error and ICC. So we can kind of see as we go down the root mean squared error, the SaO2 ranges, we start pretty accurate and then it slowly gets worse. So at 70 to 80%, we're at almost like an 8% difference between the SaO2 and SpO2. And so overall, we have a 4.13% difference between the two, which based on the ISO protocol is too high. And then our ICC value is actually pretty good. So it's 0.837, which actually falls into the excellent agreement category. Again, in showing why we had so many different statistical methods, because they all tell a bit of a different story. Okay, getting into our correlation and Bland-Altman plots. So on the left in panel A, we've got a correlation plot with SaO2 in percent on the x-axis, and then Polar Elixir SpO2% on the y-axis. The blue dots are the data points between 90 and 100% SaO2, green is 80 to 90%, and then red is 70 to 80%. And so as we can see, the line of unity would be perfect agreement. So if all our data points fell on the line of unity, everything would be perfect and we could go home. But this is, we can see that as we go from blue to red, it gets farther and farther away from that line of unity. And in particular, it actually is above the line of unity, showing that the SpO2 sensor seems to be overestimating, like we saw in that time series graph. And then if we, backing up, the Pearson correlation is quite high, 0.92. Like I mentioned, you could have a high correlation, but that does not mean it's an accurate device. And then now going over to our Bland-Altman plots. So we've got the mean of our two measures on the x-axis, the difference between the two measures on the y-axis. And so we can see that the red dots that are denoting that 70 to 80% SaO2 are above that mean difference line, showing that we're overestimating pretty regularly on that end of the scale. And our mean difference is about 2.5%. So, the SpO2 monitor seems to be overestimating oxygen saturation by, on average, by 2.5%. Okay, so the original Polar Elixir algorithm has now been validated. So next we wanted to see if we could recalibrate the algorithm with SaO2 data and make it better. So this is that exact same time series plot from before, but we've just added the new recalibrated signal on it. So the old Polar Elixir signal is the blue curve, and the new one is the kind of pink curve. And so we can see that the recalibration seemed to have worked. We seem to have mitigated that overestimation and brought that curve down to match both the fingertip pulse oximeter and the blood data. So back to our root mean squared error and ICC values, I included part A here just so you can compare and contrast. So we can see that at that 90 to 100% range, but exactly the same. And then as we get more hypoxic, we get better root mean squared error values, specifically at that 70 to 80% range. And so therefore, because we improved those those lower ranges, we've improved our full overall root mean squared error, and we went from a 4.13 to a 2.67, which is now below that ISO protocol threshold. And then again, if we look at our ICC, it was already an excellent agreement before, and it's even better after the recalibration. Correlation blend open plots again. So the gray data points and line on that correlation plot, as well as the gray blind open plot, are the exact same correlation blind open plots as the part A ones before, just rather than in blue, green, red, just in gray to compare the two. So we can see that the black data points and black line of best fit are the part B recalibrated signal, and it's closer to that line of unity, especially at those more hypoxic ranges, which is great. And our Pearson correlation coefficient got slightly better from 0.92 to 0.94. And then if we look at our Bland-Altman plots, again, that Bland-Altman plot is the same as before with that overestimation in those more hypoxic ranges. Whereas when we go to part B, we've condensed all those data points within a smaller, narrower limits of agreement. And our mean difference is now a 0.52% rather than a 2.5% from before. So lots of graphs and data, but hopefully we showed you that we validated this device and sensor to be accurate based on the ISO standard. So under a root mean squared error of under 4%. This algorithm was improved using SaO2 data. So this kind of goes to show that making an SpO2 sensor or algorithm, you should probably use SaO2 data to begin with, because it is the gold standard. One thing to note that I haven't mentioned until now is the Polar Elixir was initially created using that fingertip pulse oximeter data, which we already know pulse oximeters aren't the gold standard. So by using the gold standard, we were able to improve the algorithm. And although we didn't have enough power to actually statistically look at the difference in skin tones across the data, we were able to validate the sensor and the algorithm across a range of skin tones, and we didn't have any outliers. So that means hopefully the sensor can be used on a range of skin tones and be trusted to be accurate. And then finally, one thing we've learned from Trevor and from my lit review for this project, all SpO2 monitors are actually more inaccurate during hypoxia, which is silly because that's why you have them. We don't really know why, but that's it. The fact that the Polar Elixir does become a little bit less accurate the more hypoxic you get is right in line with every other pulse oximeter on the market as well. And you may be thinking, okay, this is a sport watch, you're gonna be doing sports with the sport watch, and you take SpO2 measurements playing sports rather than just lying supine on a bed. And the answer is actually no. There's almost no pulse oximeters out there that you can use during exercise because these measurements use optical sensors, and the optical sensors are incredibly sensitive to movement artifact. And so I think every company out there has this on their radar and are trying to figure out ways to take SpO2 measurements during exercise. So this is my wrist, and it's on the market now. This is the Polar Vantage V3. It was released about a year ago. I'm wearing it right now. Very exciting. This was the first device released with the Polar Elixir technology in it. Picture on the left is me using it to track the hike this past summer, and the picture on the right is what the graphics look like while you're doing your SpO2 test. I wouldn't recommend actually conducting it this way. You should be very still, sitting down. But regardless, it was just really cool to be part of a project where you watch a sensor go from development stages and help it reach the market and is now available to consumers. So, and actually own it, so that's cool. Okay, so really quick, I'll go over this little side project. This was a side abstract that Christian, Trevor, and I whipped up for submission to ACSM this past May in Boston. And essentially it came from, we were looking at figure 1 in our paper. And we were looking at, Christian actually was the one who noticed, and he was looking at panel B. And we saw that the standard deviation bars changed drastically as you went from not hypoxic to increasing levels of hypoxia. So essentially, we were curious, and Trevor thought this was a really interesting question. So we decided to write an abstract titled "Arterial Oxygen Saturation Variability Increases During Stepwise Steady State Inspired Hypoxia." And the objective was essentially just to observe this increase and see if we can figure out why this is happening. So we had 3 variables of interest, the first being obviously arterial oxygen saturation. This was our outcome variable, what we looked at first. And then we looked at alveolar ventilation, which is essentially just the gas exchange happening at the alveolar level. And this gives an insight into the hypoxic ventilatory response mounted by the participants while they're becoming hypoxic. And then the last variable is the arterial pressure of oxygen, or the PaO2, as this is one of the variables that drives oxygen to bind to hemoglobin in the first place. So to statistically test the heterogeneity of variance, we used the Levine's test, and I'm sure lots of you have heard of the Levine's test, and it's often used to test assumptions before running main analyses, but we used it on its own. And essentially, it tests the null hypothesis that the variances in 2 different groups are equal, and it's essentially just a one-way ANOVA conducted on the deviation scores. And so if your p-value is less than 0.5, your variances are significantly different. So how we went about this, instead of the last study we had, we kept all 5 blood draws at every stage included. We actually just averaged the 5 blood draws into 1 SaO2 value per FiO2 stage. And we did that for the 3 variables we were looking at. So we ended up getting 28 data points for 28 participants per FiO2 stage for each of the 3 variables. We ran a main overall Levine's test to see if there's any differences in the first place. And then we did a post hoc Levine's test comparing each FiO2 if the main overall one was significant. I'm only going to be reporting if reporting the hypoxic stages versus baseline rather than all the hypoxic stages versus each other for simplicity. So, okay, so another 3-panel figure. So across all the x-axes, they're all fraction of inspired oxygen from 21% down to 12%. In panel A, we've got alveolar ventilation in liters per minute. In panel B, we've got pressure of arterial oxygen in millimeters of mercury. And then in panel C, we've got our arterial oxygen saturation in percent. So if we just look at the data, this is totally what we expected to happen. When someone becomes hypoxic, they are going to mount a hypoxic ventilatory response. So the alveolar ventilation is going to go up. As much as you try to protect your oxygenation, your pressure of arterial oxygen in your blood will go down. And then obviously, as we saw in the previous study, your SaO2 response will be SaO2 decreases as well. However, when we looked at the variance, so we have each of these figures shows range, maximum and minimum. So the range, the variance didn't change statistically in alveolar ventilation or pressure of arterial oxygen. But as we saw before, it sure does in the SaO2 measurements. So basically, we're still back where we started. There was no increase in the variability of alveolar ventilation, which meant that there was no increase in the variability of the respiratory rate. There was no increase in the variability of the pressure of arterial oxygen. So what else could be causing this increase? Obviously, genetics is always a valid guess, but we're still wondering about this binding to hemoglobin thing. And the pressure of arterial carbon dioxide is actually another factor that drives oxygen to bind to hemoglobin. I got a little tutorial on this from Trevor, so I'll attempt to give you guys a tutorial as well. So this is an oxyhemoglobin curve. So we've got pressure of arterial oxygen on the x-axis, and then we've got hemoglobin saturation, or essentially SaO2 in percent on the y-axis again. So if our red curve is the regular response, response to hypoxia, then the blue curve is if you have high pressure of CO2, carbon dioxide, in your blood, you've got a lower hemoglobin saturation. Then if we go up to the green curve and you've got a lower pressure of carbon dioxide in your arterial blood, then you've got a higher hemoglobin saturation. So we're wondering if maybe there's an increase in the variability in this variable that could explain the increase in the variability in the SaO2. Open to discussion if anybody has any ideas on that. So to quote Trevor from last week, if you were here, inherent inter-individual variability may be instructive to understand the incidence and severity of altitude sickness. So everybody who goes up to altitude probably wants to know if they're susceptible to altitude sickness, and it's hard to know until you get there. And so if we can understand the variability in this response and maybe try and be a little proactive about it, might be able to help mitigate the extent to which people get altitude sickness. This is a picture of my poster I brought to ACSM. And some of you might have been there. If I saw you, awesome. If I didn't, so sorry. And then this is a picture of me with my poster. As a lot of you know, I did my master's during COVID. And so this was my very first in-person conference. And I was just incredibly grateful to be given the opportunity to go present some work, but also just to go and learn and be incredibly overwhelmed by the number of smart people in one building. So as all of you are very aware, research is such a team effort, and the study was huge. And there's we wouldn't have got it to where it is now without any of the people on this slide. So a huge thank you to everyone listed here. And then huge thank you to you guys. This is a picture of our data collection team on the left. And this is one last plug for our paper, if you want to go check it out. It's just really cool to see your name in a journal. So anyways, yeah, so thank you for coming to another hypoxia talk. I know it's different from usual, but I hope you learned something. I know I did. So thank you so much.
Do we have any questions to start with? Sure, Venus.
Very nice talk, Monica. Thank you. I'm wondering about the recalibration.
Mhm.
How was it exactly done? And is it from the data, just from these 28 people, or you need to increase the data? And so, yeah.
Yeah, great question.
Include more people.
Yeah, great question. So because Polar is a company that has products, their algorithms are all very proprietary. And so we have no access, we don't know what their algorithm looks like. And that's fair enough. Garmin and Apple have their own as well. And I don't think any of them are going to disclose that anytime soon. But from what we were told is their algorithm is kind of a regression. And so by sending them some SaO2 data, they were able to change the coefficients and the constants in their regression to be more accurate and give more accurate values at those lower hypoxic states. Yeah.
Okay.
Yeah.
And with your data, just the 28 people that you did, and
Yes.
it made that big of a difference.
And it was actually only half of that, so we only sent them 13 people.
Oh, yeah, that's,
Yeah.
because that's for the other
Right.
one for validation.
Yes.
Okay.
But of course, it probably would get even better if you sent them more and more data. But we wanted to try and keep a separate set that was blind to them so that we could really show that it was an unbiased validation and recalibration.
But you know, it's an optical, like they measure the optical, it's an optical sensor.
Yes,
basically.
100%. Yeah. Mhm.
Just to follow up on this one, so did you send them the raw data from the watch or just a result of SaO2 and SpO2?
Good question. And they had the raw results from the watch already. But we sent them the SaO2 from the blood. So we sent them like all 20, I guess each participant had 25 data points of SaO2 data. At each of the FiO2 stages, there was 5. And so we sent 13 people worth of SaO2 data to them. And then they had the raw data from the watch so they could kind of match them up. Yeah.
Do you know which frequencies of light the ABG uses? Like some of them will use like red, infrared, or green.
It was a combination of both from what I remember.
Reddit and Brett.
Yeah.
Oh, I know what their equation is, that's fine.
You wanna write a better algorithm or?
I mean, it's a ratio of like the AC/DC component of red light divided by the AC/DC component of the infrared, so that ratio, and that's your x-axis, and then let the y be the blood oxygenation, and that's the pressure.
Right,
But then they obviously had to adapt it, because it's obviously not accurate at like lower. I mean, most of them, like that relationship doesn't hold with lower.
Correct. Yeah.
So we got that, yeah.
Yeah.
Okay.
right.
Are you sure that the algorithm only considers the optical sensor data? Cause the easiest thing would be like fit a polynomial to that kind of behavior, right?
Right. I think I know
They have
that.
other things, like there's age of subjects and sex of subjects, like, do you think that any of that gets thrown in there?
I don't think so.
And the other question is, does the inter-subject variability in the relationship, or I guess just, does the inter-subject variability in SpO2 go down after the validation? Or does the inter-subject variability stay the same?
So, the variability of the SpO2 would be mirrors the variability of SaO2.
That's AO2.
Yeah.
Okay,
So it'd stay the same, I guess.
it
Answer
stays
the
the same. Okay. What about, can I ask about this Fitzpatrick date?
Sure.
So you used it because you thought maybe there's some evidence to suggest that the skin tone influences the accuracy of the, did you see that?
So so we didn't assess it statistically. I think that would be a really important study to do. But because we had a range and we looked at our data to see if there was outliers, like for example, if one of our participants had very dark skin, if we had looked at their data and they were kind of way out of line with everyone else, then maybe that would indicate maybe the sensor isn't good with those kind of skin tones, but we didn't see that. So we're hoping that it's good for all skin tones.
So to follow up on the sensor and how it works, so does it, like the other variables, have like that window where it like learns your skin tone, or like how does it, like, is it a change in the skin tone color, or how is it optically measuring that, the change?
So the sensor itself has no idea what your skin tone is. It just knows how much light, it basically, I don't know, you all are probably wearing a watch right now. There's little lights on the back of your watch face and the light gets sent into your artery. And then depending on how much blood is absorbed or reflected back, that indicates how much oxygen is in that blood. So it doesn't really, it would only know how much light gets reflected back regardless of what your skin tone is, I guess.
Okay.
Yeah.
To follow up on this, so you do not enter any data into your sensor, like sex, age, height, weight, because also if you have more fat or something, so you do not enter any data, just the
Well,
reflection.
mine knows my birthday and my sex. So I guess hypothetically it could, but I think, I don't know if that would really help the algorithm in the first place. I feel like the sensor itself, the optical sensor head with the light being sent into your blood and being reflected back out doesn't really have much bearing. Like your age and your sex don't have much bearing on that. I don't think, from my limited knowledge.
What about the amount of fat, for example, under the skin, and so,
It's a great question. It might be, I would expect it would be less accurate because there's more stuff in the way. But we didn't even take wrist circumference or anything. I've read studies that do take wrist circumference. Does that really indicate how much fat you have on your wrist? Not really, but that would be an interesting thing to look at if you had took like a DEXA scan or something, for sure.
the variability, maybe.
Yeah.
Okay.
Colin?
Yeah, some thoughts on your abstract here. So if you go back to the one where you're showing the variability, but back a few more.
Yeah.
Part of it, is it not just the stability nature of the oxygen association curve, like you can hyperventilate all you want, KO2 will increase, so you're not gonna go above 98% saturation. So the variability is fixed at that point. Versus that 70%, it's steep, so you're gonna have a lot of variability.
100%.
But that explains all of it.
it may explain part of it. And we actually had this discussion internally, actually, it's called the Simpson paradox or something like that, where yeah, you've got the ceiling effect on that 100%. For sure, that could definitely be a huge factor. I think anecdotally, while we were collecting data, there were some people that even at 12% never dropped below 90% at SAO2, and some people went all the way down to 70. And so I don't know if that's related to the ceiling effect. I think that's generally like how that person was able to protect their oxygen saturation.
Yeah, I mean, the other part of it is that you know your hypoxic ventilator, so it's vary 200-300% hour to hour. That's not even between people, so I mean, that's incredibly variable, it's not surprising at all. When you get both the hypoxic ventilator response and hypoxic ventilator decline phase without CO2 in the plant, so I mean, it's hitting your variability, right? So I mean, I would suggest probably be done under isoreactive conditions.
Right.
To start minimizing these things and very stepwise, not dynamic system.
Do you have any other, do you have any thoughts on why this is happening?
Yeah, we can talk later.
Okay. That'd be great. Trevor's been keeping us in suspense. He's like, oh, Paolo will know. Paolo will know. Any other questions?
I have a question,
Sure, Brent.
but I totally lost it. Okay, can you explain, like some of the risks associated with arterial blood draws? I don't really think I know. I mean, I assume it's just, there's a lot more pressure than the venous blood draw, so it can
Yeah.
get more messy or something, but, what are the risks? What are the dangers? So why can't we just do it right now, right here?
I mean, you could. Finding the artery, I think, watching the respiratory therapist and these anesthesiologists finding the artery looked very difficult, first of all. Second, it's quite uncomfortable, like it's quite painful. So they inserted a little bit of lidocaine in there first because it actually is quite a painful procedure. And then when they take it out, our respiratory therapist applied so much pressure to the area because arteries would just go, right?
Okay.
Rather than, veins would kind of seal themselves up a little bit, so, but yeah, no, Trevor's done, I don't know if he's done studies, or if I've read about studies that did like femoral arterial blood draws, and that would be really scary. Yeah, so those are the main reasons I would think. I've heard, and they
So
bruise,
pain and just bleeding.
pain and bleeding, and
Okay.
finding the arteries hard, yeah.
Oh, okay,
Yeah.
along the same lines, it looked like, at least for the N=1 that you showed in the very beginning for the validation data set. There was a very nice relationship at the lower oxygen levels between that little thing they wear on their finger and the SAO2 measurement. And so I think you said that the company originally developed the initial algorithm using a little finger thing. So was that just that one subject that showed that nice relationship at 70% or whatever? Because otherwise I would have just thought it would work
Yeah.
really well.
Good point. Yeah, very good point. No, so I think all participants showed that. So the fingertip pulse oximeter was significantly more accurate than everything else. I think I actually have we did, in the paper, we analyzed the fingertip pulse oximeter also. And where am I? Here it is. So with our correlation, Glenn really, really good. And so you're right, you think that if they had made their algorithm using this, it would be pretty good. But from what we knew when we talked to Polar, I think they only had access, or they only collected SpO2 data from the fingertip pulse oximeter up to 80%. And so hence why, once participants got below 80%, went off the right a little bit.
Yeah.
So,
Is the fingertip method generally a lot better than the watches? And why is that?
great question. I actually know that's about. There's two different kinds of pulse oximeters. We're all wearing watches and they're reflectance pulse oximeters. So like I said, shines light into the blood, light gets reflected back to the receivers on the watch. But the fingertip, because it goes on either side of your finger, it's a transmission pulse oximeter. So it shines light through your tissues all the way to the sensor on the other side. And so the reflectance ones are way more sensitive to any sort of movement artifact at all. We noticed when we were doing data collection, like if people were talking, it impacted the measurements, even if they were lying really still. Whereas I think the transmission ones are way less sensitive to those movement artifacts, so.
Cool. Thank you. Aaron, you have a question.
Can you go back to the slide with the N of 1?
Yes, I can. How do I? do that? Oh my god, that works. Oh god. Oh,
Oh, alright.
did I just, there was a few
What is this?
Thanks so much. Okay. You want the one with both part A and part B?
Well, just with the graph of SpO2 every 4 minutes with the blood draws. Yeah,
Oh.
that one.
This one?
So to me, it looks like O2 saturation continued decreasing during that 4 minutes. So how did you define steady state?
Yeah, good question. We kind of looked at literature and kind of saw what they used as far as the time to steady state. But we also used, the lab chart, application that we had all the respiratory variables coming through it. So we could see end tidal oxygen and end tidal CO2. And so we kind of looked at when those leveled out. Instead of the SQ, as you can even see, so we have the fingertip pulse oximeter displayed. So we could see what they were at any given time. You can see even that's like incredibly variable. And so if we had based, I don't think we could have based steady state off of the pulse oximeter, because it's just, yeah, the measurements are so variable. So that kind of answers your question. Sort of.
Yeah, well, because I'm just thinking like, if there was a way to do it like participant to participant and wait for them to plateau and take blood draws, like, do you think that would be, there would be a different result?
I don't know if it would change the result. I know we talked about maybe trying to do that, like just monitoring the participant and saying when they reach steady state, whenever they reach steady state. But they could have been hypoxic for like, this was about half an hour. They could have been hypoxic for like an hour if it had taken a long time. And our anesthesiologist, respiratory therapists were really nervous to leave people at 12% for that long. So, that's kind of why we decided not to do that. It might be, you might have less variable, SpO2 and SaO2 data. But our SaO2 data isn't too bad, I would say, like the little red asterisks, if you can see them, they're not, when you get more hypoxic, they get a little crazier, but that's because what we talked about was the variability, so. But yeah, no, it's a good point, could be worth trying.
So I have a question about the study actually. When you start at the beginning, you mentioned something about using these watches to diagnose something like sleep apnea and all that, you know. But in your study, have you ever considered like the sleep position and the accuracy of the watches? Because I see that you talked about how the subjects were in supine rest during the measurement, so they're probably laying on their back, I'm guessing.
Yeah.
So like, I know sleep positions can vary from individual and between each individual. Have you ever considered how the wash accuracy would be affected if let's say individuals are like sleeping in different positions other than supine?
No, it's a good question, and I'm sure like some people are super restless sleepers rolling around, and that would probably impact your SpO2 data as well. Generally speaking, if you're trying to diagnose or monitor sleep apnea with an SpO2 monitor, it's with a SpO2 monitor given to you by your doctor. And so I think I wouldn't recommend using your sport watch to do that. So it'd be a very specific pulse oximeter meant for that. That would hopefully be able to account for those things. So, yeah.
Do you know if there's a difference between your left arm and right arm for SO2?
Good question. We threw around a lot when we were talking about the protocol. We were gonna try and have a device on both wrists and arterial blood draws on both wrists. And it was just, that was just gonna be too much. Yeah, and the arterial, catheter was already really uncomfortable. So the idea of putting a watch, you have to wear the watch pretty tight in order for it to work. And so so if you were to put the watch really tight on top of that catheter, I think it'd be incredibly uncomfortable. But I did read a study, that did a very similar validation study to this on a watch, and they did have two watches. I think they only had arterial blood draws on one side, but, they compared the SpO2 data from side to side. And I think there was some differences based on people's circulation, and I could see how, like, you know, like your capillary layout is a little different and whatever, but, I think the differences were minimal enough for them to say that there isn't a tangible difference. And so taking measurements from arterial on one side, SpO2 on the other side is still reasonably, safe to assume that they're the same. It's a good question though. Yeah.
And second one, more like stats questions. What kind of ICC did you use?
You remember, Christian?
Yeah, I was, on my head, like a 1-3, I think, so.
Yes,
Single
you're right.
measures, absolute agreement, lots of correlation.
You approve?
Doesn't matter, we're all insensitive.
Okay.
Okay.
Follow up on
Yeah,
this.
Tina.
So what do you think about the ISO, like threshold as a
Hmm.
researcher, let's say?
Yeah.
Do you agree with 4%, for example, for the RNSP?
I'm brand new to this area, to be honest, so, I mean, the ISO protocol was like our holy grail for this study, and so I've always just kind of held it on a bit of a pedestal, and if they say they've obviously done the research and, or maybe they haven't, maybe they just chose 4%, but I'm hoping they've done the research to show that 4% was chosen for a reason. I think if you were to think about it and you know, if we're all at 97% right now, if it was at the upper end of that RMSE scale, 4%, so 93%, 100%, I feel like that's a small enough range for you to not be worried, if that makes sense. Yeah. Any final questions, Samantha?
Okay, we'll end our seminar there, and if you have any questions, I'm sure she'll be able to answer them after, and thanks again for presenting.